Hi, my name is Jacob Schaefer, Chief of Software at Gears Inc. We programmed our robot in Simulink to make use of its graphic interface and ability to simulate a program before it's deployed on hardware. Our program this year is designed to give our robot, the R11A Rafa, the ability to drive throughout the field, pick up and push cells, and deliver vaccines. The robot's control is divided into 3 subsystems according to the major divisions of its structure. All of them are linked to this one, the extra control subsystem. This subsystem houses the extra controls we added to our program to improve user interface. The first is left-handed control mode, in which several buttons switch sides with the gamepad. To prevent accidental activation, it is not entered unless 3 buttons are pressed in sequence. Another extra feature is precision mode, which halves the output to the drive motors for finer control over the robot's movement. The third and final feature is simulation mode control. During a simulation, operators can use a Logitech or Xbox gamepad to simulate the input of the VEX controller. We also included virtual controls for cases where a gamepad is unavailable. Now I'll turn it over to Daniel Beatty for a look at the drive subsystem.
Our robot uses a 2-wheel tank drive. We used a gamepad joystick to control each drive motor. These deadband blocks neutralize slow inputs from the gamepad to help extend battery life and reduce motor noise. The values from the joysticks go to these switches, which cut the values in half when precision mode is activated. The values are then sent to the motors, one of them being inverted for the right motor, since it is on the opposite side of our robot.
Let's take a look at the ARM subsystem. These gamepad buttons are used to raise and lower the arm. The signal from these buttons first goes to this switch, which disables this function when they are used to activate left-handed control mode. The values then go to this stateflow chart, which regulates the arm's acceleration for smoother movement. This value is then sent to the arm motors, being inverted for one motor. Now we'll examine the claw subsystem. The signal from these gamepad buttons is sent to this stateflow chart. It toggles between 2 positions for each side of a robot's claw, which is actuated by these 4 servos. This year we included a subsystem that provides a 3D simulation of our robot as well as an autonomous option. Now let's hear from Joshua Youngquist for an overview of our autonomous program.
Here is the code for this year's virtual autonomous run. This stateflow chart right here contains the system of commands we use to control the virtual robot used in the Best Autonomous Challenge. Within this stateflow chart are 2 overall subcharts. This chart keeps track of the score and controls the lamps in the virtual world, while this sequence of subcharts controls the robot. These subcharts, which contain the commands which control the outputs of the robot, use only cell type and compass angle to decide which steps to complete. This sequence branches out up here after retrieving the first cell, and down here after retrieving the second, allowing the program to follow the most efficient path based on the cell array. This is an updated version of the program that won the autonomous challenge within our hub.
Now I'll finish with the modeling portion of our program. This portion of the model combines 3D models and Simscape's physical networking to simulate a physical robot in a virtual environment. After connecting our CAD models with joints and adding physics, we connected the virtual robot to the Bravo's control algorithm to produce a complete virtual recreation of our robot. This concludes the presentation of our Simulink model. Thank you for watching!